Hello and good day to you all. Good morning, good afternoon, good evening. It's good afternoon, isn't it, really, in the UK here. Welcome to Code at Home episode 5. Really glad that you could join. I hope you're having a good day today and keeping safe and staying in. Let's get started. Just in case we've got some new viewers, either live or watching the recording, welcome. Everybody is welcome. Especially beginners, and let's figure out where we left off last time, and so we can dive straight in. So what we're doing at the moment is we're taking a bit of a diversion from where we've been so far, which was to look at a couple of project Euler problems relating to numbers, and we started looking at sentences and words. And what we did was to start to get a feel for how we might analyze sentences and pull all sorts of different statistics. This is where we left off last time. So if you were around last time, that's great. You can go to your Code at Home 4 or whatever project in the Replit website you've got. Just before I went on YouTube Live just now, I've created a new Code at Home 5 REPL in Replit. You can do that as well, or you can continue with the other one. It doesn't really matter. And don't forget, I'll always make these REPLs available. Let me just remind you where that is. You can always find the main link or the main blog post, which is linked in this URL here, bit.ly code at home. That'll take you to here. And then there's a link in here. Find a summary list of the past episode recordings with links in this one. And that will take you down to the episode list. And the one we did on Friday afternoon is here. Okay, and you can see there from Friday's episode, we got a link to the Code at Home number 4 REPL, which is what we created together last Friday. So I've got that one, Code at Home 4, and I've made a copy of that and called it Code at Home 5. So we can continue to modify that. So we've always got like a nice reference to what we did on a certain day. Okay, so I'm really glad you're here. What we're going to do is continue a little bit with this sentence analysis, some sentence statistics, so that we can learn about a few more really cool array functions that you can call on an array. We looked last Friday at sort, which we can see there, and we also looked at map, and we'll look at map and sort again in a bit. Okay, so let's get started. If you want to type along, then grab hold of the Code at Home 4 and start modifying that. I think we're good to go. One thing we did look at last week was the following. In fact, let me just go back to where we were last week, because I set you a bit of a question to ponder over the weekend, and that was, if I get rid of this map statement, you don't have to type this if you don't want to. If we just log out, and remember last week we just made a sort of an alias for the console.log function here, and we called it L. So we just have to type L when we want to call that console.log. The words dot sort, when we print that out, or when we run that, what comes out is a so-called sort of sorted list of words. But we've got the brown dog extremely fox jumps lazy over quick the. And what I said was have a think about why it might be sorted that way. Now, I'm sure if you did think about it, you'd realize, of course, that it was something to do with the fact that this was a capital T. Okay, and the beginnings of these words were all sort of lowercase. So that's uppercase T, and these are all lowercase letters here. And when you sort something alphabetically, in our heads as humans, if we're looking at, a simple sentence, we might not specifically spot any difference or want to spot any difference or care about any difference between whether a letter is uppercase or lowercase. There's an uppercase T, there's a lowercase t. However, if you think about how a computer works, of course it's got to distinguish. Of course a capital T is different to a lowercase t. And that has a bearing on the default behavior, that's the word we use on Friday, of the sort function. Now, there's lots of different ways we could sort of figure that out ourselves. Actually, the way that sort works is that it sorts it sort of, well, I'm going to say alphanumerically, because that's basically the alpha characters, the letters and the numbers and other things as well. Actually, it's a little bit more complex than that, but for now, we're just going to think about letters and numbers. Well, in fact, we're just going to think about letters for our case, because we've just got letters in the sentence. And it uses a code table called UTF-16. Now, don't worry about that. Don't worry if you don't know what that is. UTF-16 is sort of like a super complex version of something you may have heard of before. You may not, it doesn't matter, called ASCII, American Standard Code for Information Interchange. Very old code for representing letters and digits and other symbols with numbers. And I've got a little ASCII chart here. It's from lookuptables.com. And it looks quite complicated. However, if we have a look for the letter T, the capital letter T from let's find that. That is there. Okay, T in decimal. Okay, we don't worry about the hex or the octal or the HTML rendering. In decimal, that's 84. Okay. Now, the lowercase t, let's look for the lowercase t. There it is, 116. Okay. And in fact, if we go back to here and we see that capital T comes before the lowercase b, we can confirm that as well. Capital T, what was that again? That was 84, and the lowercase b is up here, and that's 98. Oh, I just realized that my face is in the way of the T, isn't it? Let's make that a little bit smaller. There we go. You can see that now just temporarily. I'll make it smaller so you can see it. There's the lowercase t, and that's 116. There's the lowercase b, and it's 98. So basically, what sort is doing, more or less, is taking the words and then looking at the letters and looking at the codes for the letters. It's going to be in UTF-16, but for us, let's just think about it in ASCII. And then it's going to say, well, is the code for this letter larger or smaller than the code for that letter? So we can find out about codes for letters in our REPL. So if you want to play along with me, go to the REPL, the black REPL here, the black background, and just hit clear. Okay, press enter if you don't get the little prompt. And now just say, type the string A. So open single quotes, capital A, and then close single quotes. Dot, are you ready for this? Char code with a capital C at 0. Now, what the goodness is that? Well, that's a string. The A is a string. And there's, just like there's plenty of functions that you can call on arrays, you can call functions on strings. There are specific functions that work on strings. To uppercase is one, for example. Now, this says, give me the character code, give me the decimal code for the character at position 0. And of course, position 0, we already know by now that we also always start counting at 0 in arrays, and of course also in individual characters in strings. So position 0 is exactly that A there. So give me the character code at 0. And what it tells us is it's 65. Now let's just double check. Let me go across to the ASCII table again. Let's find 65. There it is, 65A. 66 is B, 67 is C, and so on. Let's just double check. Make sure we get 84 if we go for a T. Char code at 0, 84. Now, to us humans, A comes before T when you're sorting, doesn't it? We know that anyway, because we know the alphabet. But the way that the sort mechanism works here, the behavior is, well, is 65 less than 84? Yes, it is. So that's what's happening. So now when we reconsider what we get when we call words.sort, let's just press Control Enter or Command Enter to run that. Now hopefully we understand why this word that begins with a capital T, an uppercase T, comes before all the other words, because of course, it first of all starts at the first character, and the first character is 84. So of course that's going to be a lot smaller than any other of the codes for any other of the first characters of these words. And that is why it's sorted like that. Remember then when we said, okay, well, let's map the shout function across all the words so that they're all made uppercase. Now if we run that, we can see that correctly, as it were, in our minds correctly, B, D, E, F, J, L, O, Q, T, T. That's alphabetical order, because all the letters are in the same block in the ASCII table here. A all the way through to, well, just a little bit further down there. It's not showing on my screen. Z. So that's how it works. Now, just one more thing so we can introduce. Oops. I got my foot caught around the headphone cable. Oops. Hope I haven't broke it. I should stop messing around my seat, shouldn't I? There we go. So why don't we just do one more thing before we leave this so we can see with our eyes what the codes are. Now, what we need to do, if we have a word like brown, for example, how would we display all the individual codes for those letters? We know how to get a code for a letter because we can use the char code at. And by the way, if you're interested in going the other way, if we say here, we said this before, didn't we? Let's go here. Let's clear the screen. A char, code at 0, at position 0, we get 65. If we had the 65 and we wanted to convert it into an A, there's another function, a generic string object function called string.from char code 65. What do you think that's going to give us? An A. Okay. Now, let's move on then to work out how we might say, instead of brown, let's work out how we get, for example, I'm just going to make this up now, 65, 77, whatever the character codes are for each of the letters, B, R, O, W, and N. Those are not the right ones, but that's what we want to do next. So let's go here. Now, we don't need this. We can get rid of these log statements here, words in a sentence and first and last words, because we've done those already, haven't we? So let's get rid of those so we got some more space. And also, we don't want to see the length of the first word. We don't even need the first word, so you can get rid of all of that. Okay, we'll leave that in for now, just so we've got a reference to it, that for loop, but keep it commented out there. And we'll leave the shout function definition as well. Now, just to try something out, if we've got a string, like, for example, the, and we want the individual letters, there's a special function that works on a string, and that function is split. Now, if we run split with no values at all, passing nothing, we just get the word the again. But bear in mind, we don't just get the word the, just like we saw something like this last week, didn't we? We not only get the word the, we also get the word the inside an array. It creates an array. Split will create an array. And what split does effectively is say, chop this thing up that I'm working on, in this case, the string the, chop it up every time I see a nothing. So it's not going to chop it up at all. But if we say every time we see an empty string, basically the things that are in between the letters T and H and E, sort of, what do you think we're going to get now? T, H, and E as separate letters in an array. So can you see where we're going with this? Now we can use that split as follows. Let's comment that one out for now. And why don't we say log out, let's just use the for now, split. Okay, this is a great way of working things out. So have a play around. We play around in the REPL first with a black background, and then when we sort of worked out roughly what we want to do, then we can go to the editor and start adding our code. Because don't forget, the stuff that you type in here is not saved when you go away from this Replit. The stuff that you type in here is, of course, saved in index.js. So now, if I run that, of course, we're going to get the same thing, T, H, and E in an array. However, remember, we've got the beautiful map function. Now, why don't we have the word, I don't know, let's think of a word, code in lowercase. Let's put that in there. If we run that, we get CODE in lowercase because we just split up those characters. But now if we pass the output of split, which is an array, and call on that output our wonderful map function, which is an array function that works on an array, and we map the shout function over that array, as in the shout function that we've defined last week, just converts anything it's given to uppercase, you can guess what we're going to get, can't you? CODE in uppercase. Okay. Now, we can use that little pattern, .split.map, to then call this char code at, can't we? Okay. Let's define it as a separate function here, const get char, let's just call it code. Const code equals, given a letter, okay, let's call it L. What does our function need to do? It needs to return the evaluation of letter dot char code at 0. Just like we did over here. If we said, let's say this was the letter dot char, oops, I typed that chat, not chat code, char code. Char code at 0, that's going to give us 65. So we're doing the same thing inside this function here, this function called code. Whatever we pass it gets captured in the L parameter, and then L dot char code at. Now, let's just take a moment and say, well, we've got this W, the parameter name W here, and yes, we're sort of using W because we're sort of in our heads thinking it's going to be a word that's going to be passed to us. And we've got the L here because we think, it's going to be a letter L passed to us. But actually, we don't have to call those parameter names according to what we might get in. we can be a little bit more general, a little bit more generic with our function definitions. Okay, just make it easier on our brain so we're not having to think about, oh yeah, what shall I call this parameter? And it's quite common when you're defining little helper functions like this, rather than have a meaningful, a letter that has a meaning like L for letter, or rather than have a variable name that has a meaning like L for letter or W for word, we just call it X. Have you been in maths at school where they've said, let's think of a number and let's call that X? That's sort of what we're doing here. Let's just call in both of these functions. Okay, the functions will work exactly like they did before. The function doesn't care what the parameter name is called, X or W or L or anything. So let's call them X. So our code function expects a parameter X, and it will call char code at 0 on that X. So now if we replace that, let's have a look what happens. I think I'm going to change the string here just so we're not confusing ourselves. Okay, why don't we call it, I don't know, banana? Okay, in programming, most programmers, most coders have their own favorite test word. Banana is my test word, my favorite test word. So I'm going to use banana. So I'm going to run this now. Let's see what happens. Wow. Okay. So in fact, we've got how many letters in banana? 6 letters. How many elements in this array? 1, 2, 3, 4, 5, 6. And in fact, we can sort of see a pattern already, can't we? 97, 97, 97. That's the same letter, effectively. That's the same code. Now, let me make it a little bit easier. Let's just do the uppercase version because the numbers are smaller. 65. We've seen 65 before, haven't we? That's the letter A. 65, letter A. 65, letter A. So we've got letter B, 66, 65, 78, 65, 78, 65. B, A, N, A, N, A. So now we've got a great way of looking at the individual character codes for each of the letters in a word. So why don't we now think, I'd like to be able to use that. So let's go up here and create another function called codes, plural, equals X again. And in this case, X is going to be a word because we want all the codes for all the letters in a given word. So what we need to do is we need to say X dot split exactly what we've got. In fact, rather than type it in, just to emphasize, all we need is that bit. So I'm going to copy that. I'm going to paste it in there, and we want X in front. Now, just in case you're all typing along with me, I'll give you a couple of seconds to type that in. And for those of you, once you've typed it in, just stare at this for a minute. I find when I'm coding and I see a piece of code that I'm not quite sure about, I stare at it and let it sink into my brain, and then I understand it. So what this is doing, this codes function, is saying, well, it's expecting something, let's call it X, and it's going to call on that, whatever's in X, it's going to call split with an empty string, open quotes, close quotes, single quotes, these are. That will give us an array of the individual characters in that X, in that string. And of course, then it will call map on that array. And each time, for each element in that array, map will call code. So give me the code for that first element, give me the code for that second element, given the code for the third element, and so on. And can you see as well, we're sort of building our program up, building our code up bit by bit with little building blocks. So we've got a function here called code, and then we're using that function in this function here. Now, let's get rid of this line. And now, let's have a look, shall we? Words, map, codes. Okay. Amazing. Now, I wonder... No. Let's pretend I didn't do that. So now we can see, it's almost like seeing the skeleton of these words. Now we can see the individual codes of each of the letters. Okay, there's the, there's quick, there's brown, and we can obviously spot extremely because it's the long one. It's there. So hopefully we've now got a little bit of a better feeling, a better insight on as to what's happening behind the scenes on a sort and what's happening behind the scenes on letters and strings. Okay, now let's move on. Now we've got this split function and we understand what it does. Remember last week when we looked briefly at this Project Euler problem number 4, largest palindrome product. A palindromic number, okay, we're still dealing with words and letters, but it doesn't matter. A palindromic number reads the same both ways, okay? So how would we, given a word like banana, how do you think we might use split, for example, and some other functions to work out, to get the computer to work out and tell us whether that string was palindromic or not? Now, we as humans, we can tell that that's not palindromic, that's not a palindrome because it doesn't read the same forwards as backwards. There's lots of words in the English language that are palindromes. Can you think of any? Apart from the single letter words, that's a bit of a cheat, right? That's a palindrome because it reads the same forwards as backwards. A. How about the word level? That's a palindrome. L-E-V-E-L, L-E-V-E-L. How about the word noon, middle of the day? That's a palindrome as well. There's all sorts of palindromes. So what we'll do is we'll change this now. We'll change this sentence for one with a few palindromes. You know, we're human. We can put a little test sentence together. How about, and I want you to type this in as well, in uppercase, all capitals, the race car. You've got to spell it like that, otherwise it wouldn't be a palindrome. The race car sounds a little bit sort of funny, but let's just call it race car. Drove on the level road. That's a silly sentence, isn't it? Oh, at noon. There we go. So we know that we've got 1, 2, 3 palindromes in there. Now, how do we figure out which of those words are palindromes? Now, we don't need this anymore either, so let's get rid of that. But we still need the words, okay? And let's leave these we might need these functions. So let's leave them in for now. Let's get rid of that. Okay. So what you want to do now, if you're typing along with me, you still want this const L equals console.log. You want to change the sentence so it says the race car drove on the level road at noon. We'll have the words as well. There's that split, and last time we split on a space, remember? And then we've got these three functions that we've defined. Okay, so in our mind, maybe what we do to see if a word is palindromic, let's take the word the. Let's put these in a comment so it doesn't get executed. What we do is in our mind, maybe we split that word up, and then we think about what those individual letters would be in a reverse order, E, H, T. And then we sort of join them back together again. We get rid of the dashes. And then we think, okay, well, is this thing the same as this thing? Maybe that's what we're doing in our minds when we're looking at a sentence and seeing if we can pick out some palindromes. And we can tell from that the isn't a palindrome, is it? Let's do the same thing. And again, anything I type in comments, you don't have to type in. This is just for illustration purposes. Let's go for noon. So first of all, what we do is we split the letters up. And we know how to do that, don't we, with split. And then we reverse those letters. So we take this one first, and then this one, and then this one, and then this one. So we write them out, we join them together again. And we get that. And then we say, well, is that the same as that? Yes, it is. So that must be a palindrome. Now, remember, as a human, we can do that in the blink of an eye or a click of a finger even. But we've got to tell the computer how to do that with code. So that's what we'll do, okay? Because we'll need to know in solving this problem, and the problem statement is find the largest palindrome made from the product of two 3-digit numbers. Don't worry about the second half of that sentence. The first half is what we want to concentrate on. Find the largest palindrome. That is going to involve generating some numbers somehow and then having a look at those numbers and seeing if they're palindromes. And for our purposes, of course, numbers and words are sort of the same. They've got letters. They've got numbers instead of letters, but they've got essentially elements in an array. So we need to work out a way, given a number or given a string, whether that number or that string reads the same back to front and front to back. Okay, so let me get rid of those comments there. In fact, I'll bring those back for a second and let's do that here in the REPL directly. We start with the. Then we have to break up the letters, don't we? And we can do that with splits. We've done that already. Look, let's see what happens. We get T, H, and E in an array. It doesn't matter that it doesn't look like that. We've got those letters split up. Now, what's the next thing we do? We reverse those letters. Funnily enough, it just so happens that there's another array function called reverse. And what do you think happens? If we've got an array like 1, 2, 3, let's just write it out literally, dot reverse Don't forget it's a function, so we need to supply the open and close brackets. We don't pass anything to the reverse. We get 3, 2, 1. Don't worry about whether there's spaces or not. We just get 3, 2, 1 from 1, 2, 3. So actually what we can do, don't forget, that will give us an array of 3 letters. So if we then say dot reverse, what do you think we're going to get? EHT, which is exactly what we want here. But of course, we want to eventually compare what we've got with the original string. Of course, we're going to eventually compare what we've got here with the original string here. So we sort of need to squish those back together. We need to join these letters back together. We've split them apart and reversed them, and now we need to join them back together. Funnily enough, there's also an array function called join. If we've got an array with 3 strings, and the strings don't have to be single letters. You could have, for example, apple, there, banana, carrot, dot join. If we call it with no parameters, it will default to joining those 3 things, all the elements of that array, with a comma. Sounds nice, doesn't it? What happens if we pass the sort of same thing, the empty string that we use to split, the thing that's sort of theoretically in between the T and the H and in between the H and the E? Sort of, in my mind, that's the way I see it. Why don't we try and say, we'll call the join function on this list of strings, this list of words, but instead of passing it nothing, we pass it the empty string. And the empty string is not the same as nothing, of course. What do you think we're going to get? Apple, banana, carrot. But that's exactly the sort of effect that we want, isn't it? So now, if we go back up to here, where were we? There we go. The dot split on an empty string, and then reverse, we get that. So then if all we say is, because reverse produces an array as well, so we can use the join array function on that. And if we say whatever's in the array produced by reverse, join those things together, join those elements of the array together with no space, no nothing, just squish them together. That's what we get. We get exactly this string that we want to generate so we can compare it with the original string. Okay. So now, what happens if we now start to bring this bit of code from the REPL, let's copy it. Oh, in fact, let's type it out together rather than you fight with a copy paste. Let's go back up here. Let's leave that thing there, right? So why don't we say, let's call it, let's call it backwards. Let's call a function backwards. Const backwards, a backwards version of a string, is a function that takes something in X, and all it's going to do is evaluate the following: X dot split on an empty string, split on an empty string, dot reverse. Don't forget, each time we do a dot something, it's calling a function, isn't it, with the brackets, dot join on an empty string. Let's just move that across there so you can see it all on one line. So we're defining a function called backwards that takes something in x, and the first thing it does, well, it'll evaluate that whole thing and produce and return whatever that produces. So what does it do? Whatever's in x, it'll call the split function on it, specifying the empty string, which will split whatever's in x into individual letters in an array. So it'll produce split will produce an array. Reverse will reverse all the elements of that array, and then join will squish together all those elements of that reversed version of the array. So let's try that, shall we? Let's just try it first of all. Let's log out the call to backwards. To the string hello. Why not? Are you ready? Ole. I think that's hello in some strange language somewhere. It must be, mustn't it? But anyway. So we've now got a function that will give us the backwards version of a string. So now we can really easily define a function that will check if a word is a palindrome or not. Now, let me move. We don't need that anymore, do we? So let's just put that there. Okay. Do you remember in episode 1, we defined a function called is multiple of 3. And we also defined a function called is multiple of 5. And then later on, we defined a function, I think it was maybe in episode 2, is even. The is part of the function name was important to us because it sort of told us by convention that the sort of value that we were going to get back from calling that function was remember the word? Was a Boolean value, was a value that was either going to be true or false, nothing else. So when we're writing a function to tell us whether a word is a palindrome or not, it sort of makes sense that we also want to call that function is something, is palindrome, because there's only two possible answers, isn't there? Yes or no, true or false. So why don't we say const is palindrome equals. So we'll define a function called is palindrome. Can you guess what's going to go in here now? Well, first of all, we're going to pass it something in x. And all we need to do now we've got backwards, is to say, let's evaluate whether x, whatever's in x, whatever that string is that the same as exactly equals to, remember that equals, is equal to, very strict, is equals to. Just tell me, evaluate whether whatever's in x is the same as whatever the result of calling backwards on x is. Now, let's try that with a couple of words. Log is palindrome of the. And also, let's log out is palindrome of race car. Okay. What do you think we're going to get? Well, we know that this is an expression that's evaluated and will only ever return a Boolean value because of this operator here. Now, I'm using all these words, but we're all super good already to understand what these words mean. This is an operator, a strict equals operator. Is something equal to that or not? Yes or no? True or false in computer speak? So we know that the result of evaluating this expression is only ever going to be true or false. So we're going to get true or false in each of these things here, in each of these outputs. Let's try, run. false for the first one, true for the second one. Let's just double check. Let's try this with something else as well. Let's try it with banana. False, true, false, of course. But if we change banana to level, remember, that's a palindrome. We can tell it's a palindrome. False, true, true. So now we've got a function that will tell us whether what we give it is a palindrome or not. And we can use that now to start solving Project Euler, problem number 4. Now, before we do, let's finish this one off by getting this code here, getting our code to pick out just the words in this sentence that are palindromes. So we want it just to tell us the words that are palindromes. So we're expecting it to tell us race car, level, and noon. Let's get rid of these little log statements for now. We've already split up the sentence into these words here. Okay. So let's use that words. So let's log out the words first of all. Start from basics. Okay, so far so good. Now, there's one more, well, there are plenty more, but there's one more function, array function, that I want to introduce you to in this session. And it's sort of like the brother or the sister of the map function. There's some other brothers and sisters as well, but this one is the one we want to look at right now. And that function is called filter. And as you know, in real life, a filter lets certain things through and stops other things getting through. Like a sieve, you know, if you're cooking and you're filtering something through and you want to sort of keep all the bits and pieces and have the nice juice coming out, a nice gravy, and you're filtering all the lumps out of the gravy. Because when I make gravy, it's very lumpy. So filter works in exactly the same sort of way. It keeps things from getting through and it just gives you what you're looking for. So filter, just like map, is what we're calling an array function, as in it works on arrays. And we know that words is an array. We know, first of all, because we know how we produced it with the split function, and we know split produces an array. But we can also see with our eyes right here that words is an array with these little square brackets. So let's call filter with no arguments, first of all, with no parameters. Let's not give filter anything. I've actually no idea what's going to happen. So let's try it. I'm going to hit Control Enter. There you go. There's another error. But it's a good error. Remember in the previous episode on Friday, we had some sort of reference error. This time, we haven't got a reference error. Remember, always start reading. Never be worried about the errors. You know, it's trying to help us. Always start reading from the top here. And the first thing it says is type error. Undefined is not a function. What does that mean? Well, if I tell you that just like the map function, the filter function expects to be given to it a function. And that function that we give to filter is a function. It's almost like a little testing box. So filter works through each of the elements of the array it's called on, one at a time. It takes the first one, for example, puts it through the function that we pass. And if that function produces true, as in yes, then it lets it through, lets that value through, and we get that value out the other end. But if the function that we pass it into returns false, then it doesn't pass it through. Okay, let's just see what that really means. In fact, remember, yeah, we've got time. Remember, let's just comment this out for a second. In a previous episode, we defined a function called isEven, didn't we? Const isEven equals x, take something and return whether x modulo 2 is 0. Okay, remember that from a couple of episodes ago. So isEven is a function that takes an x, let's say a number, divides that number by 2 and checks that the result of dividing that number by 2, as in the remainder, checks that equals 0. And if it does equal 0, then of course it nicely, cleanly divides by 2, and therefore the number must be even. Now, if we have a range of numbers, 1, 2, 3, 4, 5. In fact, let's log those numbers out first of all. There they are, 1, 2, 3, 4, 5. That's an array here. So we know that we can call filter on it. Guess what we're going to pass? Guess what sort of function? Well, guess what function? The function we're going to call on it is even. Now you can all probably guess what we're going to get, don't you? Can't you? Let's run it. 2 and 4. So what's happened is that filter function, we've given that filter function a so-called, I'm going to use a funny word, but you might see this. It's called a predicate function. Bit of a strange word, but a predicate function is just a function that will either give you true or false. It's like a, yes or no, you decide type function. Okay? It's not a function that calculates numbers or words or anything else and gives you back some sort of weird result. It's a function that it will just give you either true or false. It's called a predicate function. So the filter function here is expecting a predicate function, a function that gives back a true or a false. And our isEven function here is a predicate function because that will only ever evaluate to true or to false. Great. So what happens is that filter says, right, okay, let's go. And it takes each element of the array that it's working on, that it's being called on here, takes 1, for example, first of all, and it passes 1 to isEven. And isEven will spit out either true or false for that, won't it? And of course it spits out false. 1's not even. So the result false from calling isEven on the first element of the array means that that first element doesn't get through the filter, doesn't come out the other end. Then it takes the next element of the array, 2, it passes 2 into isEven, gets out the result. This time it's not false, it's true. So filter allows 2 to pass through to the other side. So we get 2 as the first value in the resulting array. Then it calls 3, passes 3 to isEven, that gives false, so it doesn't let 3 through at all. Then it passes 4 to isEven, gets true, because 4 isn't even, of course. So it lets 4 pass through to the other side, so there's 4 comes through here. And then it passes 5 to isEven. Of course, we get false from that, so it doesn't let 5 through, it filters it out. So that's how filter works. So now we understand how filter works, let's delete that, remove those comment marks, and now I think you can guess which predicate function we can use to give to filter so that it will only let through to the resulting array those words, those elements in the words array that are palindromes. course, it's the is palindrome function. Okay, are we ready? Let's try that. So what we're wanting this to give us are only the words in this sentence. Of course, we've split the words already, that are palindromes. Let's see if that works. Well done. Have you got that as well? I hope you have. Let's just move this to the right so we can see that other one all in one line there. Now, I think we've done really well. So let's finish today's episode just by going back now to the project Euler number 4 and just having a think about how we might start to solve that in the next episode, which is of course on Wednesday this week. Same time as always, 3:30. By the way, we've been talking about letters and numbers and sentences and basically strings here. What we're talking about here in Project Euler problem number 4 are numbers. But you'll see when we come to Wednesday together that we can still use exactly the same sort of techniques to work out whether a number is palindromic or not. Look, there's a palindromic number. Reads the same backwards as forwards. So what I want you to do between now and Wednesday is have a think, not about how you can work out whether a number is a palindrome or not, because we more or less know how to do that now. We've got a function that will probably help us out a lot. What I want you to think about is what's been happening here on this example. Remember, Project Euler problems usually give you like a really simple case first of all. The largest palindrome made from the product of two-digit numbers is 9009, which is 91 times 99. In other words, we need to, first of all, if we want to sort of double check that for ourselves as the first thing we do, we need to work out how do we generate all the different products of two-digit numbers. Don't forget there's two number twos there, two-digit numbers. So a two-digit number is a number with 2 digits. So what's the smallest two-digit number? If some of you might be saying 00. And if you said that, thumbs up to you. But let's just do some more normal maths that we might have in school. And the lowest two-digit number is 10, isn't it? What's the highest two-digit number? 99. So we've got a range of numbers from 10 all the way through to 99. Twice two-digit numbers, because we've got to make a product. Don't forget, a product basically means just the answer when you multiply these two numbers together. So we've got to check, for example, 10 times 10, 10 times 11, 10 times 12, 10 times 13, 10 times 14. Each time getting the product, getting the answer, and seeing if the answer is a palindrome, and then working out which of those is the biggest. So eventually we've got 10 times 98, 10 times 99. Okay, right. 11 times 10, 11 times 11, 11 times 12, 11 times 13, 11 times 14, 11 times 15, blah, 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 11 times 99, 12. So you can imagine even doing two-digit numbers is quite tedious. Okay. But also, did you notice that even in that little example I spoke out there, I was sort of repeating myself? The first question to ask yourself is 10 times 11 the same as 11 times 10? And if it is, we don't have to do both calculations, do we? Okay, so until Wednesday, have a great time, stay indoors, keep safe, wash your hands, and think about how you might generate the products of two digit numbers. Okay, until then, bye.